Hi, welcome to lesson 14.6 where we're going to talk about tangent planes and differentials. Let's dive right in. All right, so what we've got here is a picture of a surface in blue here, and the tangent plane is this pale pink, and we have a point P naught that is on the surface, and that's the point at which the plane touches the surface. So they've drawn the gradient vector of F, which is the surface here. And notice they've couched it as a level surface. And so that's going to matter in a little bit that you notice that this equals a constant. So this is a level surface to a function of an additional dimension, okay? So pay attention to that as we go through and the way it changes. So we have other vectors that lie in this plane, and they've drawn them to help you realize that the gradient vector would be orthogonal to all of the vectors through P naught that lie in this plane here, okay? So we have a vector valued function here, and because we skipped unit 13 and we'll be going back to it, we may not have seen this very often yet, but this is a function r of t, and the components are all functions of t, okay? So the x component is a function of t, and so are the y and z components. And so when you plug in a value of t, then you are given coordinates for a position vector that points to a point on the curve that is the vector valued function r of t. Okay, now this is a position function, like the motion of a particle along a curved path in space. And so we consider it smooth, and we express the level surface of this curve as a function of x, y, and z, which equals a constant. We always are going to consider f a differentiable function in all of these setups. And so if we actually take the derivative with respect to time of our vector valued function r of t, which f of r of t, so there's our, right here is our level surface function, okay? And we're going to get this expression, which we'll look at in a moment. But I want to ask this question down here at the bottom. Since f is a constant and equals c, then the derivative of a constant would be 0. So that makes this gradient f vector of r of t dot r prime of t, this is a dot product, that equals 0. So we've got a special situation where the gradient of f is going to be orthogonal to the velocity vector of our vector valued function. So this is just a little thing to point out here. Since this expression would end up being 0, we know these vectors are orthogonal. So the level surface, the gradient of f here, is going to be orthogonal to r prime of t, which is going to be like one of these vectors down here. Okay, so it doesn't make a whole lot of sense yet until we dive in and do something with it. But with the understanding of what this picture is, we're going to focus on the various curves that go through P naught. So they've got some drawn here, okay? And the plane normal to our gradient, this pinkish kind of plane here, must have all of the velocity vectors through P naught, okay? Because they're all orthogonal to the gradient of f. And so we have a definition that we can work with here. The tangent plane at the point P naught on the level surface, the blue level surface, f of x, y, and z equals c, of a differentiable function f is the plane through P naught normal to the gradient at P naught. So if you'll recall, the equation of a plane is always going to be the normal vector, get my pen, the normal vector dotted with P naught P. This was our generic definition, equals 0. So these are vectors, and because they are orthogonal to each other, their dot product equals 0, and this is what gave us our generic function for the equation of a plane. If you'll recall what this equation is, because you're going to see a lot of setups in this section that look like this. So you want to remember the equation of a plane. Okay, and then that makes n the vector ABC, and the difference between P naught, which is x naught, y naught, z naught, and P, which is x, y, z, these would be the components of the vector P naught P. Okay, so I want you to remember that setup for the equation of a plane because we're going to have a formula for this now. Okay, so the equation of the tangent plane, notice we've got f sub x evaluated at P naught, f sub y rather, evaluated at P naught, and f sub z evaluated at P naught. That would be the orthogonal gradient vector. Remember, the gradient of f is the partial of f with respect to x times I, and the partial of f with respect to y, j, and the partial of f with respect to z, times k. Okay, so there is another notation for the partial derivative, and we're evaluating it at the point we're interested in. And then this would be the vector that goes from P naught back to P, okay, in the picture, and we are doing the dot product here, and that equals 0 to get our equation of a plane. And necessarily our normal line to this same curve at that point would have a very similar format. We see our partial derivative evaluated at the point in each x, y, and z equation with the appropriate direction. Then we see our initial point, P naught, as the constants in each of these, and the parameter t, and this would be our parametric equations of a line for the normal line to our level surface at a given point. All right, so we want to see how this looks in action, and so we're going to need the partial with respect to x, and that's going to be 2x. Okay, so find the tangent plane and the normal line. So both of these, and both of these require us to find the partial derivative. So that's my first thing to go do. F sub y is going to be 2y, and f sub z is going to be 1. Okay, we need to evaluate these at the point 1, 2, 4. Okay, so we're going to have x is 1, plug it in here, 2. So this is f sub x evaluated at P naught. So I'm actually getting the whole coefficient value here, and for each one of the others. F sub y is 2y, which would be 2 times 2, which is 4. F sub z is just 1. It's a constant in this case. And now we need to use these as the coefficients of our parenthetical expressions. And it's just positive 1, okay. And this is going to be x minus x naught, y minus y naught, and z minus z naught. Okay, cleaning this up, 2x minus 2 plus 4y minus 8 plus z minus 4. It's going to be 2x plus 4y plus z is negative 14, so moving that over is positive 14. So there's the plane. And here's a picture of what we just did. We found the equation of the plane that is tangent to this surface at 1, 2, 4. All right. Now, to write out the normal line, no more calculation is needed because we have each of our partial derivatives evaluated at P naught already. So if I can write on the bottom here, x is going to be x naught, which is 1, plus f sub x evaluated at P naught times our parameter. And the y parametric equation is going to be y naught plus f sub y evaluated at P naught, which is 4 times our parameter, and z is going to be our z naught plus f sub z was a constant, so that's 1 times t. So here's the parametric equation of the line that is normal to the surface. So we would have a line coming outward making a right angle. So they've actually tried to draw it here. So this is coming off the surface making a right angle with this plane. All right, so moving on. The question is, are we limited to level surfaces? That's not always going to be convenient if all we have to work with are level surfaces. So we need to take a step back and say we want an equation to help us find a tangent plane when we're given a surface of two variables, not a level curve for this, but the actual surface at that point. And z is a function, so z naught is a function of x naught, y naught. So we're going to basically plug this into, we're going to do some manipulation here, okay? Actually, that was a little too soon. So what we've got to realize is that I could rewrite this expression as z minus f of xy equals 0. And now this is a function of x, y, and z. Notice I'm using capital F. Okay, equals z minus f of xy, which does equal a constant. So now I've kind of got a level, I've turned my surface into a level surface of some function that I don't know yet, okay? So I'm going to take a step back, work with big F, all right? So now, be good. So now, I'm not going to make you sit and watch me write all this out, but if we take the partial of capital F with respect to x, that's d dx of our little function right here, and that's going to be f sub x, and then the derivative of z with respect to x is 0. So big F sub x is the same as little f sub x. Same story for f sub y. We're going to have little f sub y minus 0, so the derivative with respect to y of the original function is the same as the capital F function. And then df dz, partial with respect to f of xy minus z, is just going to be -1, because we don't have a z in f of xy, so the derivative of negative z is just -1. And that gives way to this equation. So yes, these are cut and pasted images from the book, but I'm afraid that a lot of times people read it, but they don't really take it in. So that's why I'm going through some of these in this section. So we're going to use our partials of capital F with respect to x evaluated at p naught, with respect to y, with respect to z. This is our generic formula for finding the tangent plane for big F, okay? And we figured out that big F sub x is little f sub x, and big F sub y is little f sub y, and big F sub z is just -1. So we need to do our substitutions here. And it produces our equation. So little f sub x evaluated at p naught times x minus x naught, and so forth. And notice there's no partial with respect to x here, or with respect to z here, rather, like we might expect to see because of this equation here. But when we did this and we created big F of x, y, and z by manipulating this equation here, we end up with just minus z minus z naught. So that's where people insist on putting in f sub z and doing a calculation that doesn't belong here, and that's the one place that people tend to mess up. So we're going to use this now and get some practice in so we know how to use it. All right. So here we go. Here's our sample problem. We've got the plane, but we want to find the plane tangent to this surface. Now, this is z expressed as a function of x and y, okay? And we're going to use the point 0, 0, 0. That makes the math super easy. And so we know that big F sub, if we subtracted z and set it equal to 0, we would be working with a big F function. And we learned that big F sub x is just f sub x. And we're going to go with that idea from the derivation on the previous screen. Okay, so we're going to evaluate this at 0, 0. Okay. So the partial derivative with respect to x is going to be cosine y. And then over here is going to be y e to the x. And then we need to evaluate it at 0, 0. And that's going to be cosine of 0 is 1. Minus 0 times e to the 0 is going to be minus 0, so 1. All right, keeping track, making sure I'm getting these right. Okay, f sub y, evaluated at 0, 0. Derivative of this expression with respect to y is going to be, let's see, negative x sine of y minus e to the x. And we're going to evaluate that at 0, 0. And that's going to be 0 times sine of 0 minus e to the 0, which is negative 1. And then f sub z, we learned, is going to be negative 1. Okay? And so now we are going to plug these into our formula. We're going to have 1 times x minus 0 minus 1 times y minus 0 minus z minus 0 equals 0. So this one cleans up really easily. X minus y minus z is 0. And there is our plane tangent to this surface. All right, I like it when there's zeros. It makes a lot of calculations super easy. Okay, example 3 is a little more involved, but I want to make sure that you understand the setup here because we have a very similar calculation, but we don't have a very simple definition of our ellipse. So we've got two surfaces, f of x, y, and z, which is our big cylinder here, okay? And then we've got a plane cutting through the cylinder at an angle that creates this ellipse right here. And so we want to find parametric equations for the line tangent to this ellipse E at the point 113 right here, okay? So notice they've given us some hints in the work here. We need to find gradients and we need to cross them because that would give us a vector that is, okay, so I want you to see the setup here. The tangent line we're going for is orthogonal to both del f or grad f and grad g. And so if we do our cross product of grad f and grad g vectors, we're going to get that tangent vector, okay? We can then use that vector to find the equation of the line tangent to that ellipse at the point 113. So here we go. So we're going to call the vector in this direction v. That's going to be grad f cross grad g. So we've got to find grad f and grad g first. Okay, so remember partial derivatives with respect to x, y, and z. So 2x I, and then 2y j, and there's no z in there, so we're done here, but we want to evaluate this at 1, 1. And don't bother with the 3 because there's no z in this expression, but we're going to have 2i plus 2j. So that's this vector here. Then we're going to have grad g, and with respect to our the partial derivatives with respect to x, y, and g here are going to be even simpler. We're going to have 1i, so I can leave the 1 off. There is no y in this expression, so partial with respect to y is 0. Partial with respect to z is also 1. And since there's no variables in this expression, we have our grad g. And now, in order to find v, we're going to have to cross grad f and grad g. Now, I want you to remember a cross product gives you an orthogonal vector to both vectors. So it can only be done with vectors in 3 space, so you have to put in a 0 here. Okay. I really should have put a k here because we took the derivative with respect to y and got 0, with respect to z and got 1, so this should be a k. So this vector is going to be 1, 0, 1. Okay. So to save time, so you don't have to watch me go through this, this comes out to be 2i minus 2j minus 2k. I know these videos are long. I'm doing what I can to shorten them. And so here's what we know. Where this vector right here is our cross product right here. That's in the direction of the tangent line. So that's going to help us set up our tangent line. The other thing is we've got to go through the point 113. So our line in parametric form is going to be our starting point, x naught, plus our x component 2 times t. And then our y component is going to be our y coordinate of p naught, 1. And then in our direction we get from our v vector times t, and z, we start from 3, which is z naught, and we go in the direction of our cross product vector, and we come up with our parametric equation. All right, so See, there was a good deal of setup here in order to get a vector that's in the direction of the derivative of the line that we were seeking. So we're not stopping here saying this vector is tangent to the ellipse. We want to know the actual equation of the line tangent to the ellipse. All right, so in single variable calculus, you used estimates, you used differentials to help you determine the change in little bitty pieces along a function. And so we use differentials, and whenever we see df or ds or dx or dy, we know that means a little tiny change, not a big one. So if we want to estimate the change in a function, we're going to call it df, okay? And since we're in functions of two variables, we're going to do it in a direction u. And I want you to understand that u has to be a unit vector, which is not the most obvious fact in this little setup. And in fact, I've told you before that I actually do a little hat over unit vectors so that I don't forget their unit vectors. And that's very helpful right here because they didn't say it. They just said in the direction of, which means you have to cut it down to a unit vector to use it. And nowhere in this problem did they say that. So I'm hoping that you're paying particularly good attention right now. So let's just kind of pick this apart. We have the directional derivative, the gradient of f evaluated at p naught, dotted with the direction in which we're taking the derivative. So this would give us a directional derivative, which gives us the rate of change in the direction of u. And then this is actually the distance, the length. Remember, s is the variable for arc length. And we will get back to chapter 13 and pick that apart some more. But we're just going a little distance along the arc length, and it will be multiplied by the rate of change. So rate times distance, okay, distance traveled and how fast we traveled is going to give us our incremental change in our function f. All right, so here's our function f down here. We want to see how much the value of this function is going to change if the point xyz moves 0.1 units away from our p naught value. So here's our starting. Remember, sub-zero means the point position at time 0. So we're starting at 0, 1, 0. We're moving 0.1 units away toward this other point, 2, 2, negative 2. So they didn't hand us u. We had to figure out u. So u is going to be p naught p1. Okay? And I haven't cut it down to 1 unit yet, so I just need to get this vector. Now, if you really hate the ij's and k's, I'm going to do it without that right now. So if I find the vector components going from p naught to p1, that's going to be 2 minus 0, and 2 minus 1, and negative 2 minus 0. So we just got the basic components of u, but we need the length of u to cut it down to a unit vector. So 2 squared, 1 squared, and I ignore negatives. When you square things, they go away. That's going to be the square root of 9, which is 3. Okay, so we've got to cut this down to be a unit vector by dividing everything by 3. So we have 2/3, we have 1/3, we have negative 2/3. Okay, so now we want to dot this with our gradient vector. So we need to take our gradient, we need to figure out what grad f is, and then we need to evaluate it at p naught. Okay, we've got the derivative, partial derivative with respect to x here is going to be y cosine x. Okay, told you I was doing this without the ijk, so equals, and here's my vector bracket. All right, derivative with respect to y is going to be sine x plus 2z, and with respect to z is going to be 2y. So here is our gradient vector. We've got to evaluate it from our starting point, 0, 1, 0. All right, so plugging in some pretty simple numbers. We've got y is 1 times the cosine of 0. Well, the cosine of 0 is 1, so 1 times 1 is 1. And sine of x, sine of 0 is 0 plus 2z, which is 0. 0 plus 0. And then 2y is 2 times 1, or 2. So here's our gradient vector evaluated at the point 0, 1, 0, and now we've got to dot those together. So grad f evaluated at 0, 1, 0, dotted with unit vector u is going to be, and maybe I should change colors just to help out here, 2/3 times 1. And remember, a dot product is a scalar quantity. 1/3 times 0, and negative 2/3 times 2, it's negative 4/3. So we get negative 2/3. And now we go back to our formula and plug our numbers in. The change in f is going to be our dot product times our change in distance along the curve, 0.1 units. So this is going to be approximately negative 0.067 units. All right, make sure your answer to this question is not a vector, that it's actually a scalar quantity. Okay, so again, here's me trying to save a little time so you don't have to watch me write out all this stuff. This is from the book, and if you don't take a moment to think about it, then you're just trying to memorize a bunch of formulas that you can't keep straight because they're all so similar. So you did linear approximation in single variable calculus, and so we're going to build the idea for this in multiple variable functions using the definition of differentiability from section 14.3. The difference here is this part was on the right of this equation, so we've moved it left, and so we want to see this is the change in the function from the point xy, or excuse me, from the point x0, y0 to another point. So this is the change in the function value. And here we are, rate of change times the change in the x direction times the change in x. And rate of change of the function in the y direction times the change in y. And we've got our little extra epsilon expressions here, which actually both go to 0 as the changes in x and y become smaller and smaller and smaller. So if we've got our delta x and delta y values extremely small, then these values just don't even matter and they drop out, okay, which is nice. So we've got our approximation here, and we've got this on the right hand side again. This part is our linear approximation, okay. So moving this over after having dealt with the fact that these go to 0 gives us our linear approximation. So here it is, linearization. And the whole point of this is sometimes functions are just so complicated, especially surfaces and multivariable functions, that we would like to be able to use linearization to give us an estimate. And that's all this is. So they explain over here the delta x and delta y expressions and how they are referenced here in the change in position in the horizontal direction and the vertical direction. And that's, we've got our initial point, and then this is the change in the x direction and the change in the y direction. So we're going from here to here, and that would be our approximate value of the function, you know, in this two-dimensional drawing that doesn't really represent 3 dimensions very well. Okay, so let's give this a try. Find the linearization of f of x, y at the point 3, 2. So just making sure my notes are close by, so this is correct. So we're going to have to find the partial, you know, we need our linearization, x, y. And our answer is going to be an equation in x, y. So we're going to need the value of our function at that point. And we're going to need f sub x. So I'm going to go ahead and let's take some notes down here. F sub x is going to be what up here? We've got 2x. And minus xy is going to be 2x, excuse me, minus y. And then we've got to evaluate this at 3, 2. So we're going to have 2 times 3 minus 2 is 6 minus 2 are 4. All right, we're going to do f sub y. So nothing there, minus x there. Derivative here, bring the 2 over, that's 1 times y, so plus y, and that's a constant. So evaluating this at 3, 2, we get negative 3 plus 2, or negative 1. We also need the value of the function at 3, 2, and that's going to be 3 squared minus 3 times 2, plus 1/2 2 squared, plus 3. All right, that's going to be 9 minus 6 plus 2 plus 3. Did I do that right? Yep, and that's going to give us 8. So remember, this is our partial. I was going to plug in values up here, but I changed my mind. And now we need to fill in our known values. So L of x and y is going to be our function value. We figured out 8, plus our change, x minus x naught is x minus 3, and then our derivative in the y direction, and y minus y naught, which is 2. And we clean this up a little bit. 4x minus 12 and minus y plus 2. So L of x and y is going to be 4x minus y, and this is 10 minus 12 minus 2. So here is our linear approximation at the point 3, 2. All right, moving on. So differentials. Let's dive a little bit more into differentials, and I'm going to kind of walk you through this. If you don't read the textbook very well, or it doesn't meaning doesn't come out to you, then take this chance to kind of listen to how I do it. Honestly, I don't know that everybody has to do this, but I have to take notes. I basically have to rewrite what I'm reading in order for my brain to process it. Okay, so I'll walk you through it. So we've got a differentiable function of x and y, and all of its partial derivatives exist at our initial point. And then we're going to move to a nearby point by changing x and changing y a little. And so the change in f is our function evaluated at x naught plus delta x and y naught plus delta y, and subtracting the value at the original point. So the difference between our function value at our starting point and our function value at our ending point would be the change in our function value. So the change in x is x minus x naught. So when we substitute that in here, we've got x naught plus x minus x naught. And same thing here for delta y when we substitute that in. So we're going to use our delta L, our linear approximation. This right here is going to end up being x comma y. So the linearization at xy minus the linearization at x naught, y naught, and we can put in our linearization expression here, and then we have a little presto magic step where things just automatically change notation that really used to blow my mind, but this actually explained it well. Differentials dx and dy are independent variables, so we can assign them values, and the most frequent way we handle dx is we think of it as the change in x, or x minus x naught. And same thing for y. So when we substitute those in, okay, instead of using delta x and delta y, we use dx and dy, okay? And so the total differential is what this is called. The differential of the entire function is the change in the direction, the rate of change in the direction of x at a given point times that change in our x plus the change in y in the y direction times the total change in y. So we've got, remember, every derivative is a rate, and this is the actual distance. So it tells us how far along in this direction we get to go. So the total differential of f is what we're calculating here. All right, so let's see that in a problem. So we've got a cylindrical can, and it's designed to have a radius of 1 and a height of 5, and these are in inches. All right, but the radius and height are off, as the real world often is. The differential of the radius is it's bigger by 0.03 than it should be, and the differential of the height is it's smaller than 0.1 inch. smaller than what it was meant to be. So we want to estimate the change in volume. All right, so if you recall, the volume of a cylinder is pi r squared h. So we're going to end up needing the derivative of the volume with respect to the radius. Okay, so that's going to end up being 2 pi rh. And then we're going to need the differential in the h direction, or with respect to height, and that's going to be pi r squared. So there's our two differentials we're going to need. And there we go. So we have gradient of v is going to be v sub r evaluated at r naught h naught, and v sub h, oh, excuse me, let me take that back. I left off the differential, times dr, and then partial derivative with respect to h, evaluated at our initial point, times the change in the differential with respect to height. So here's what we've got. Our total differential, which is what we're after, is going to be 2 pi r naught h naught dr and pi r naught squared times dh. And now we just go fill in values. 2 pi times our initial radius times our initial height times the change, the differential in the radius. And pi times 1 squared times the differential in the height. And so now we're just crunching numbers. This is 10 pi times 0.03, so 0.3 pi. And this is negative 0.1 pi. All right, so this is 0.2 pi, or approximately 0.63 inches cubed. By the way, I don't need you to round functions unless you're told to, or in the case of a practical problem, whether you're asking about physical objects, real world things. I find an answer that is not left in terms of pi to be much more understandable, and it makes you feel better and know that if your answer is just grossly too big or grossly too small, that it would stick out. Okay, this teeny tiny change in a cubic inch, a little bit more than half a cubic inch, is going to result in these little bitty changes in the diameter and height, or the radius and height, excuse me. All right, I am not going to walk you all the way through sample problems for these very parallel concepts of linearization and the total differential in two variables. Notice that I have skipped the error calculation part in linearization in this section, and that's fine. I also skipped it in the assignment, so you have very similar concepts with functions of more than two variables by the addition of our third variable partial derivatives in the direction of z. So there are some of those in the homework, so make sure you pay attention to the very, very parallel concepts here when you add another variable. All right, thanks for listening.